So good morning, welcome to the memory management session. I'm Eres Petrank from the Technion, and our first talk is by Jawang Jong, Sonhu Park, Janggun Lee, Jaehu Yeon, and Jihoon Kang from KAIST. And Jae Hwang will give the talk.
Thank you for introduction. Welcome to my talk. In this talk, I'm going to introduce our new work on verification of RCU under relaxing memory using separation logic. Concurrent programming is hard to get right. For instance, here's a bug report from a popular Rust concurrency library called Crossbeam. It describes a user after free error in their concurrent lock-free queue implementation. It turns out that this bug was caused by misusing a memory reclamation library called RCU. We're not going into the details of this bug, but the takeaway is that memory reclamation adds another layer of complexity to concurrent programming, which is already complex enough. So our aim of paper is to tackle this challenge by providing a formally verified foundation for using and implementing RCU correctly. To understand RCU, we first need to see why memory reclamation is a problem under lock-free concurrency. Lock-free algorithms share data without acquiring locks to avoid contention. This is great for scalability, but it creates a problem for memory management. For example, let's consider a shared data structure with a root node and a data node n. Suppose thread 1 is reading the node n. But at the same time, another thread concurrently removes that node from the data structure and frees its memory. Now, when the thread 1 tries to access n, the program will crash due to the user after free error. So to prevent this kind of error, we should ensure that we defer the reclamation until all threads are done accessing the memory for the node n. And RCU is a popular solution for this problem. In RCU-based system, we should activate a RCU critical section before accessing the shared data. This critical section doesn't really lock the data, but it protects the data from being reclaimed. And on the other side, after we detach a node, we should call the retire function instead of directly freeing it. This function tells the RCU system to reclaim the node later when it's safe. The actual reclamation will happen only after the critical section are deactivated. So with the basic idea of RCU, let's revisit the bug from the first slide. The original bug is quite complex, so we're going to use a simpler example that shows the same underlying problem. Now let's imagine two root nodes pointing to a node n. We want to remove the node n from the data structure. So we first cut the link from root 1 to the node, and we make a critical mistake here. We forget to cut the link from root 2, and then we just retire the node n. The problem is that RCU fully trusts you, and it sees no one is in the critical section, so it decides that it's fine to free n. But as a result, the pointer from this root 2 is now a dangling pointer. So if someone follows this pointer, it will cause user after free error, even if the thread is inside the critical section. So this bug highlights a requirement of the retire function that the node to be retired must be completely unreachable from the roots. And our question is how to enforce this kind of requirement. Actually, this is the problem we already explored in our prior work at PLDI'25. In that work, we used a concept called the pointed by assertion. This is basically the reverse of the the standard points to assertion of the separation logic. So for example, in this case, we simply have root 1 points to n and root 2 points to n. And on the other side, we have the pointed by assertion that tracks all the incoming links of all the incoming pointers to n, which are root 1 and root 2. Now suppose we cut the link from root 1. Then our pointed by assertion is updated to just root 2, removing the root 1. And if this pointed by set becomes empty, we know that the node is now unreachable. So this means that we can use the empty pointed by assertion as the precondition for the retire function. In the current state, we can satisfy this precondition. So it's verified that it's safe to retire n. But in the bug example we saw a while ago, the root 2 is still inside the pointed by set. So the proof is going to fail, which means that we're going to catch the bug while we're trying to prove the code. So our verification worked pretty well, but the limitation is that we assume the sequentially consistent memory model, or simply SC. In SC, memory operations are strictly ordered. But the problem is that modern processors and compilers don't provide SC by default because SC incurs a lot of overhead. For maximum performance, they use relaxed memory consistency, or RMC. But RMC has serious implications for our verification method. One issue is that the pointed by assertion becomes dependent on the view of each thread. Let's see an example. Suppose we have a link from root to n, and we cut the link by writing null to the root. But in RMC, this write doesn't immediately propagate to other threads. So it means that the other thread may read the old value, the pointer to n. Which means that, so while some thread, that the thread that cut the link thinks that n is pointed by nothing, another thread may think that n is still pointed by root. Then our question is, what's the meaning of the pointed by assertion under RMC? This brings us to our improvements to RMC separation logic. First, to verify the uses of RCU, we designed the pointed by assertion that works correctly under RMC. And in addition, in the later part of the talk, I'll introduce our work on verification of RCU implementations. For this task, we made a new proof rule for a crucial synchronization primitive called the SFence. Let's dive into the first contribution. So we want to build a new pointed by assertion. But to do that, we first need to see how the existing RMC logics handle the points to assertion. Since in RMC it's possible to read the old values, the points to assertion now has to track the history of the values written in the location. We can think of this history as a simple list. For example, suppose the node initially points to n1, and then we write n2, and then n1. Then the points to assertion of the node R is going to be list of n1, n2, and n1. Now, let's build the RMC pointed by assertion. We're going to do this in 2 steps. So we're going to first track the old edges, including the stale ones, and then we're going to hide the edges that are observed to be stale. For the first step, we need to identify each edge, and we're going to use the identifier as the pair of the source node and the index of the pointer value inside the points to history. And then we're going to build a set of all incoming edges, which is going to give us n1 pointed by r, 0, and n1 r, 0 and r, 2, and n2 pointed by r, 1. The second step, we're going to hide the stale edges. So our end result should be that the pointed by set of n1 should be just r, 2, and for n2, it should be empty. And the question is, how do we justify deleting the old edges r0 from n1, r0 from n1, and r1 from n2? The key idea is that the overriding thread that wrote the newer edges know that these values are stale because they observe that the new value they wrote. We can model this observation as the scene assertion, which is already provided by the existing RMC logic. For example, by providing scene r,1, we can delete r,0 from the pointed by set of n1, and then with scene r,2, we can delete r,1 from the pointed by set of n2. So that's how we made RMC pointed by assertion. Then how does this apply to RCU? Well, it's basically the same as the DSL version. That is, we use the same proof rule as the same proof rule for the retire function, except that it uses the RMC pointed by assertion under the hood. So that's how we adopted the pointed by assertion of RMC and how we verify the RMC usages. Using this, we verified some log-free data structures that use RCU, including the fixed version of the queue that appeared in the bug report we saw at the start. Now, let's take a look at how to verify RCU implementations. So this is the RCU implementation we verified. This is rather complex, so we are not going to the details, but instead, let's focus on this highlighted part. In this part of the code, we first write to a shared variable, and then we execute an instruction called scfans, and then we read another shared variable. Because of this pattern, we call this pattern read after write synchronization, or simply raw synchronization. And this pattern is essential for RCU and many other concurrency algorithms. To understand how raw synchronization works, let's look at a simple classic example. This simple code snippet implements mutual exclusion for two threads. It uses two variables, L and R, both initialized to 0. The left thread writes 1 to L, and the right thread writes 1 to R. And then they read the variable written by the other thread. If they read 0, they enter the critical section. In SC, we can see why this works by a case analysis on the order of these two writes. We can see that in both cases, at least we know that at least one thread ends up reading the value 1 written by the other thread. This means that no more than a single thread enters critical section, which implies the mutual exclusion. But this property breaks in RMC because there's no strict order between two writes. Specifically, it's possible for both threads to read the old 0 values. So these both threads could end up reading the old value 0, and they could enter the critical section, which violates mutual exclusion. To fix this problem, we must insert the scfans instruction between the write and the read. These scfans instructions have a global strict ordering, and they propagate the preceding write to the thread that runs the later fences. We can see this adding fences restores mutual exclusion by a case analysis on the order of fences. Let's say the left fence executes first. Then because of the fence synchronization, the write to L becomes visible to the right thread. So the right thread must see the value 1, which blocks it from entering the critical section. And the same reasoning applies to the case, in the symmetry case, where the right fence runs the first. And our new proof rule for scfans captures this reasoning pattern. The main idea is quite simple. First, we introduce an assertion called the SC hist. As the name suggests, this tracks the global history of the SC fences as a single list. This allows us to reason by the case analysis on the order of the fences. And when a thread runs an SC fence, it can add its observation of some events to this SC fence history, which is indicated by the precondition sin E in the sin E. In the mutex example, each thread is going to add the observation that they wrote 1 to their variable. And after the fence, the thread running the fence, we're going to obtain the observation of all the prior events as indicated by the scene assertion in the post condition. In the mutex example, the right fence came, in this example, the right thread fence came later, so the right thread gets the observation of the value 1 written by the left thread. Nicely, this does the same reasoning pattern applies to RCU implementations. In RCU, conceptually, there are fences inside the retire function, and there's another fence inside the function to enter critical section. So we can consider two cases. In the first case, if the fence in the retire function happens before the fence in the critical section, then the thread entering the critical section will receive the observation of unreachability of the node, which is provided as the precondition of the retire function. So the thread in the critical section will not be able to reach the retire node. And second, if the fence of the critical section came first, then the RCU system is going to see that there can be a thread inside the critical section, which means that the RCU system is going to defer the reclamation. So that's how we, that was our SC fence logic. Using this logic, we verified an epoch-based RCU implementation we saw a while ago. We also verified a classic algorithm called the Peterson's mutex, which is another important example of using these SC fences. You can find the details of, You can find the details of these case studies in the paper. And to conclude, we made it possible to verify the realistic RCU implementations under relaxed memory using the new pointed by logic and the SC fence logic. And finally, we mechanized all our proofs in the rock prover and the Iris framework. Thank you for your attention, and I'd be happy to take any questions.
Okay, thank you for a great talk, and this is also a winner of Distinguished Paper Award. So if please state your name.
Oh yeah, I'm Derek Dreyer, Max Planck Institute. So this is really interesting work. So my question is, the SC, I'm particularly interested in the SC fence proof rule because that's something that wasn't supported in the previous weak memory separation logics. It's remarkably simple, so I'm wondering what is there something, I'm wondering why it wasn't developed before. Is it that the proof is complicated, or that it's a kind of low-level rule and it's harder to work with, or what's the catch, or is there a catch?
As you correctly pointed out, the proof rule is remarkably simple. But the problem is that the actually case studies are really difficult because you have to reason about this SC fence history, and you really need to consider all the cases that arise from the ordering of the fences. And the problem is that when you assume the general case where you run the API functions multiple times, which means in this case you have to consider more cases.
Okay.
So I think that's the main reason why there was no work tackling this the algorithms that has to use SC fences.
So I mean, does it force you to reason about sort of lots of different interleavings of these?
Yeah, exactly. Yeah.
I see. Okay, so it's a fairly low-level rule.
Yeah, exactly.
And another question maybe while you change, is it difficult to move to other data structures and maybe even to other reclamation schemes?
So actually we were doing another case study using, which is to verify the hazard pointer algorithms. So the proof rules are quite similar. So there are some portion of the proof rules that are shared between the RCU specification and the hazard pointer specification. So the main idea doesn't really change, but for hazard pointer, the proof gets a bit more complex because I think you already know about the validation, things like that, which is already complex even in the SC version. So and this exacerbates in RMC. So I think it's quite difficult to hide all the details like this inside RMC.
Thank you. Okay, so the next talk is by Janggon Lee, Jonghyun Kim and Jihoon Kang from KAIST, and Jang Gong will give the talk.
Hi, thank you for the introduction. And today I'll be talking about a brand new way to apply hazard pointers that was actually slightly mentioned before to optimistic data structures using immutability. Now, even though we have just seen a great talk on memory management in non-blocking concurrency, I'll still provide some more background, albeit with a slightly longer example. In particular, let us consider a linked list with 4 nodes. And suppose a thread T1 that was currently at node 1 obtains a reference to node 2 and wants to access it. However, the scheduler abruptly stops T1 and runs another thread T2 who wants to remove nodes 2 and 3. To do so, T1 will first detach the 2 nodes and freeze them. However, as we have seen literally 20 minutes ago, in concurrent programming, it is unsafe to immediately free detached nodes, as when T1 wakes up, it will access node 2, which leads to a use after free error. Thus, for safety, we must ensure that T1 has finished using node 2 before freeing it. There are several methods for this kind of work, for this kind of reclamation in non-blocking concurrency. A classic example, the one we have seen in the previous talk, is RCU. RCU supports majority of data structures, in particular those that benefit from the efficient optimistic traversal strategy that I will come back to later. However, RCU is not robust, meaning that its memory usage is unbounded. Another example is hazard pointers, or HP for short. Unlike RCU, HP is robust but was incompatible with optimistic traversal. In this work, me and my colleagues have developed a brand new methodology that enables to efficiently apply hazard pointers to optimistic traversal. And before getting into our main idea, I'll first explain hazard pointers in detail. Going back to the first example, let's see how hazard pointers prevents use after free. On the one hand, before T1 accesses node 2, it first protects node 2 to ensure it is not freed. On the other hand, after T2 detaches nodes 2 and 3, it does not immediately free them, but retires them, deferring freeing them until all protection is over. At this point, node 3 can be reclaimed, but node 2 cannot, as it is being protected by thread 1. Once thread 1 finishes accessing node 2, node 2 protection will be released, and it can be freed as well. However, protection alone is not enough to guarantee safe access. To see this, consider the case where T1 wishes to further progress to node 3. Similar to before, it will protect node 3 and access it. But as node 3 is already freed, this is a trivial use after free error. Thus, after protecting node 3, T1 should validate that node 3 is not yet free to guarantee safe access. In practice, this is done typically by checking that a node is not detached. This works because a node must be retired to be freed and must be detached to be retired. To efficiently check if a node is detached, we typically utilize a marking mechanism. For example, before detaching nodes 2 and 3, we mark them as to be detached, sending a warning to traversing threads. Marking is typically implemented by tagging the least significant bit of the next pointer field. After marking, a separate step will detach the 2 nodes. Now let's see how hazard pointers' standard validation strategy, which I dubbed valmark, utilize marking for protection. Again, suppose T1 wants to step from node 2 to node 3. First, T1 will protect node 3. Then, it tries to validate the protection by checking that node 3 is not detached. To do so, it checks the mark of the previous node, node 2. Here, as node 2 is unmarked, T1 knows that node 2 is not detached, and node 3, which is pointed by node 2, is not detached as well. So, T1 has successfully validated the protection of node 3 and can safely access it. Let us also see the opposite side, where a marked node causes a validation to fail. Again, we are checking that node 3 is not detached by checking the mark of the previous node, node 2. Here, as node 2 is marked, T1 knows that node 2 is to be detached and in this case it actually is, and node 3 is to be detached as well. So T1 simply gives up on trying to protect node 3 and restarts from the beginning. While hazard pointers and a standard validation strategy, valmark, is widely used, a major problem of valmark is its inapplicability to optimistic traversal strategy. Optimistic traversals are traversals that ignores marking for performance. For example, an optimistic traversal through the following list will step through nodes 2 and 3, like so, even though the 2 nodes are marked and reach 4. Now, it is not hard to see that optimistic traversals are much more performant than those traversals that restart when they see a less marked node because they simply have less restarts. Now we get to our problem, which is that a crucial downside of valmark is that it is too pessimistic to be applicable to optimistic traversal. To see why, consider what happens when you apply hazard pointers with valmark to the previous traversal, in particular when we are about to step from node 3 to node 4 on the current configuration. First, like before, T1 will protect node 4 and proceed to validate that node 4 is not detached by checking the mark of the previous node, node 3. And here, as node 3 is marked, similar to before, T1 will think that node 3 is to be detached and node 4 is to be detached as well and restart from the beginning. However, in this case, node 3 is actually still attached, so validation could have actually succeeded. And not only is this a missed opportunity for validation, but it could also be a source of live lock, which is very unideal. To resolve this discrepancy, it is a very common practice to sacrifice optimistic traversal to use valmark. That is, it is common to sacrifice the efficient optimistic traversal strategy for the robustness of hazard pointers. In this work, we have developed a new validation strategy that overcomes this limitation and can be efficiently applied to optimistic traversal. Our key idea is to leverage the inherent immutability of traversal-based data structures for validation. Now, let us look into this idea in more detail. By immutability of data structures, we mean that a marked node's next pointer fields becomes immutable. For example, say nodes 2 and 3 are just marked as to be detached. But before detachment, another thread, T1, tries to add node 2.5 before nodes 2 and 3. To do so, T1 will first create a new node and try to update the link that points from node 2 to node 3 to point to node 2.5. But as marked nodes are immutable, the link cannot be updated and the insertion will fail. Now, immutability is actually essential for the correctness of traversal-based data structures, and to see why, suppose marked nodes were actually mutable and the insertion of node 2.5 succeeded. In this case, when T2 finishes running and detaches nodes 2 and 3, we see that the node 2.5 that was just inserted actually becomes unreachable from the head node even though it has never been called to be detached. Immutability prevents such a problematic scenario from happening. Now, let us look at our new immutability-based validation strategy, valimmute, and see how it can validate node 4 in the previous example where valmark has failed. As the same as before, we are traversing from node 3 to node 4 and want to validate our protection on node 4. In contrast to before, we don't check the previous node, node 3, but instead choose to check the first unmarked node, node 1. Here, T1 will see that as node 1 is not marked, thus it can conclude that node 1 is not detached and node 2, which is pointed by node 1, is not detached as well. And here comes our key observation. During T1's traversal to node 4, it should have seen that node 2 and node 3 were marked, hence immutable. In particular, this means that T1 can learn that even without directly checking the mark of node 2 and 3, node 2 will still point to node 3, and node 3 will still point to node 4 as they're immutable. And as it has learned that node 2 is not detached by checking the node mark of node 1, it knows that node 4, which is transitively pointed by node 2, is not detached as well. Thus, T1 has successfully validated the protection of node 4 by checking the mark of node 1 and can safely access node 4, continuing its traversal without restarting. Now, let us see some experimental results. In these graphs, we compare hazard pointers with our optimistic validation strategy val_mut, colored in pink, and the pessimistic validation strategy val_mark, colored in orange. And thanks to optimistic traversal, data structures using val_mut outperform those using val_mark by a large margin, up to 24% for lists and 61% for trees. In conclusion, we see that val_mut is much more performant than val_mark thanks to the power of optimistic traversal. In the paper, we have a more detailed explanation of hazard pointers with val_mut, such as application to an optimistic binary tree and optimistic skip list, verification in the ROC theorem proving using the IRA separation logic, and detailed comparison with other reclamation algorithms. So please check it out if you're interested. And although that was quite short, that's all, and I'll be happy to take your questions.
Yeah, any questions? Can you come to the mic? And say your name and affiliation.
So my name is Ruslan Nikolaev. I'm from Penn State. Great talk. It's actually a very interesting idea, right? So we actually had somewhat similar idea when we worked on the Trajan tree, but we can talk offline.
Yes, we should talk offline, yes.
Yes, so one question I have, I glanced through the paper. So it seems like you evaluated Hurlithy-Shavit skip list,
yes.
Right? And I was wondering, did you try to evaluate Fraser skip list? Because Fraser skip list is kind of similar to, I guess, Harris list, linked list, right? So where you
yes, I think we did. Like, we did a lot, and I think for the skip list, so the skip list, so there are a few variants. I'm assuming you're talking about the few different variants of skip list.
Yeah, so there is one skip list is kind of similar to Harris-Michael list, and the other one is kind of similar to Harris list.
Yeah, I think we essentially implemented all variants, and like there's even one, if you like want the ones that's similar with Harris-Hurley-Shavit list, we implemented all of them, I think.
Okay.
We can discuss more offline.
Okay.
If you want the details of the experiment. Yeah.
Okay, thank you so much.
Yes.
Yeah, so I must say we also wanted to do this. Great idea. Can you say to which data structures this cannot work with?
No,
can
so
you,
that's
can you categorize them or just
so
give an example?
So I guess the more projects that can you like prove that it is applicable in a general sense. So we thought of doing that, and we like had a few ideas, but we decided that like the term data structure is way too broad in ours for our purpose. But we do believe that. So I guess the question is like, so we do utilize immutability. So I guess the question is how general is this assumption? And even though we don't have a formal proof, we do believe that like most data structures, especially concurrents, are essentially bag-shaped. And if you want to update them using CAS, you essentially have to utilize the marking and immutability mechanism, because or else this counterexample happens. So I believe that if you want linearizability for your data structure, you kind of have to use this immutability property, and then hazard pointers will most likely work. But as I said, we haven't done a formal proof of it or something like that.
Okay, thank you. Let's thank the speaker again. So our next speaker is Tianle Chu, and with a joint work with Steve Blackburn, both from Australian National University.
Hello, everyone. So today I'm going to talk about ISO. So in this talk, I'm going to cover the high-level design of ISO and some of its key implementations. A more detailed explanation can be found in the paper and in our source code repo on GitHub. So now let's get started. So first, let's look at what is ISO. So ISO is first practical thread local GC for Java. It implemented and evaluated in a production JVM, OpenJDK. So it solves a 30-year-old problem, which is how to do thread local GC properly for a language that cannot exploit immutability statically. And ISO can also be used or configured as a request-based GC for multi-threaded services. So I will show you later, it allows for substantial performance wins when workloads are suitable. So before getting down to the details, let's look at the motivation behind this work. So why we develop ISO? Well, GC performance remains a problem, especially for those large-scale request-based web services. Those services are often latency critical and throughput sensitive. And most importantly, some of them having quasi-independent requests, which can be utilized. And what we want to have here is a collector that has high throughput, low latency, and low heap footprint. So how should we do that? Before answering this question, I would like to show you an interesting old result from Java C. So Java C is a benchmark in spec JVM, and it was supposed to be GC intensive at that time. And however, someone found that if you set a heap size to some certain values, then all of a sudden, the GC cost is barely visible. This was very confusing, and the result was not clear until this heap occupancy graph was generated. So in this graph, the y-axis is the heap volume, or live bytes in the heap, and the x-axis is time. So we can see the heap occupancy goes up and down repeatedly. So if you happen to trigger the GC when the heap is almost empty, like those 4 points, then it's not very surprising you're going to see a almost zero cost GC. This looks very nice, and it should be applicable in the request-based workloads, right? But unfortunately, it's not, because in a multi-threaded context, thread heap occupancy won't align. So you won't be able to find a plot point where all requests have just finished their requests. So naively triggering a GC when some requests have finished is more likely to interrupt much more threads in the middle of handling requests. And this is disastrous for latency. So it looks like what we really need here is a thread local GC that allows for each individual thread to collect their own garbage without interfering with each other, right? But why no one has done this before? Well, because there's no practical thread local GC for languages like Java. Until now, thread local GC has been limited to languages with statically exploitable immutability. I'll get onto this later, but now let's briefly look at thread local GC. So these are the 2 papers from Linearizability, who first designed and implemented a thread local GC for the functional language ML. So they were very old papers. They were published like 30 years ago. So in the simplest case, each thread operates entirely independently with its own private heap. So here's an example. We have 2 threads, thread A and thread B. So you can see thread A doing a local GC, and thread B is not affected. Similarly, when thread B is doing local GC, thread A is not affected, right? This looks very nice. But actually, this is not reality, because in practice, some objects will be referenced from globals and thus become public. So what does that mean, or what challenges does that present? Okay, now we introduce public objects and public heap, which contains all the public objects. So they are represented in white circle, and those blue circles are private objects. Since now we have 2 kinds of objects, we now can have pointers from private to public, but we might also have pointers from public to private. And in this particular case, it's a publication operation, which is problematic for thread A, because it introduced race condition. So how do we deal with publication? Well, Linearizability proposed an invariant, what we refer to as the DLG invariant. It reads private objects can only be reached from the stack of the thread that allocated them. This invariant can be enforced via a write barrier that checks for public to private pointer stores. And this invariant has a very important implication. Objects can only be published by their owning thread, which means there won't be any race. So this is a high-level illustration of how to maintain a DLG invariant in the right barrier. So before you install the public to private pointer, you first make all the referenced objects public. And only after doing that, you install the pointer. So great, looks like DLG solved this problem for us. Well, not so fast. There are still issues unresolved. So how do we know all references to moved objects? So far, like public objects reside in a distinct heap. So this implies moving objects upon publication, which is problematic. Remember in the previous example, there were pointers from other private objects pointing to the objects that are about to be published. And now, since those objects are moved to the public heap, we need to fix their pointers. Otherwise, we have some dangling pointers. So the literature gives us 3 solutions. The first one is just do a thread local GC at every publication, like this. So similarly, after you copy all the objects to the public heap, then just trigger a local GC, which will fix all the pointers. And only after doing that, you install the pointer, right? But remember, we are talking about right barrier. So do a thread local GC in a right barrier. This sounds crazy, because you might end up doing millions of local GCs, right? And in fact, there are even more reasons why this is not going to work, because in order to trigger a local GC in the right barrier, every pointer store has to be a safe point. And none of the production runtime can afford to do this. So the main takeaway here, this is not a solution. So another approach is to exploit statically enforced immutability, like the functional language ML. So if objects are immutable, we can just duplicate them so that public objects will now point to the public copies, while private objects still pointing to the private copies, right? It looks fine. But how do we resolve this without immutability? Because there are many languages like Java which doesn't have this nice property. So we need to find some other solution, right? So there's another solution, or naive solution, I would say, is just use a non-moving heap. So instead of having public heap and private heaps, we just merge them into one joint non-moving heap, and public-private becomes logical rather than physical. So because no objects will ever be moved, so no pointers needs to be fixed. And similarly, when an object is about to be published, we just need to make sure that all objects referenced are published before the pointers are installed. But unfortunately, non-moving heaps are non-starter. We know they suffer from like fragmentation and bad locality. So this is a quick summary of the existing solutions, and unfortunately, none of them is working. So apparently, ISO needs to find some better solution, right? Well, a key insight here is opportunistic copying let us leave public objects in place while moving private objects and vice versa. This solves the referential integrity problem without regressing to a non-moving garbage collector. And this approach is not possible with traditional strictly evacuating collectors such as semispace, G1, and etc. So ISO is built on top of Emmix. It uses Emmix heap structure and Emmix allocator. Apparently, Emmix supports opportunistic copying, which is essential. And the bump pointer uses 32 kilobytes blocks and 256 lines. The minimum allocation unit is a single line, so it can fill in holes between live objects. And this is the high level of the heap layout. So there's no separate global heap. Every object has a public bit to indicate whether it has been published or not. And objects living in like Emmix blocks and public objects, private objects can share the same block. So when thread A is doing a local GC, all private objects are evacuated while public objects are left in place. And after the GC, you can return the free memory. Similarly for thread B, right? And eventually, one might need to trigger a global GC, which in this implementation, we force back to the IMIX. So in the global GC, only public objects are evacuated, while private objects are left in place. And by doing so, we got a more compact heap layout. So now let's quickly look at the evaluation. So this is our experimental setup. We choose 3 request-based workloads with quasi-independence. Our baseline is IMIX, since this implementation falls back to IMIX. We also compared it to G1 to ground the results in the default production GC. So there are a bunch of results in the paper, but at this stage, I just want to focus on the DLG and the publication-related stuff. This is the overhead of dynamically tracking private and versus public. So we can already see there are 3 benchmarks have extremely high overhead. Apparently, ISO is not suitable. And for those 3 benchmarks, although Kafka looks exactly fine, but it turns out to be a single-threaded workload. So there's even an open issue on the Capo GitHub. For Cassandra and Tomcat, essentially, they didn't do a lot of work. And also, Cassandra has relatively high overhead. So this leaves us with Lusearch and Spring. And we also built another compilation server using Spring. We called it Spring JC. So this is the all request time among all those 3 collectors. We can see ISO in the green improves significantly in both Lusearch and Spring JC. While for Spring, ISO is slightly worse than G1, but it is still noticeably better than IMIX. And this is the median latency, or P50. So the value for Lusearch is so tiny, so it's barely visible here. But we still can see ISO improves noticeably. And this is the P90, very similar to the previous P50 results. Right. So to summarize, ISO is not a general purpose GC. It's targeted large-scale request-based services which having quasi-independent requests. And there are 2 very important insights here. Request-based GC allows for very low overhead collection, and opportunistic copying is the key to first practical thread local GC for Java. So I just want to reiterate that. ISO is just first practical thread local GC for Java implemented and evaluated in a production JVM. And request-based GC for multi-threaded services allows for substantial performance wins if the workloads are suitable. Okay, I'm happy to take questions.
Yeah, so any questions? Please state your name.
Hello, I'm Jung Kim from KAIST, and thank you for a great talk. And I guess this ISO garbage collector can be, I guess it can be effectively optimize the virtual thread or green thread, for example, in virtual thread in Java or coroutine in Go language.
Yes.
So I'm looking forward to see that, but I'm also not 100% sure whether it will be trivially applied or not, because those kinds of virtual threads is just a user level thread.
Yes,
yeah.
Conceptually, it's relatively simple because there's not much difference between like virtual threads and the current the settings. But for the implementation details, depending on how virtual thread is implemented, there might involve a bunch of work. Actually, we were looking into this a while ago.
I see that, and I wonder whether the Dakapo benchmark you used has those kind of virtual thread benchmarking.
Not yet, because I believe the virtual thread is only usable in JDK'24. There used to be a relatively issue which will cause deadlock. So in JDK'21, so I think virtual thread hasn't been largely used in the community, I believe.
I see. Thank you.
Yeah.
Okay, maybe you can have Dan switching the computers and no, come on with the one last question.
Tomoharu from University of Tokyo. I have a question about the latency.
Yes.
So your GCC has a surprisingly short latency latency
is that latency come from the what garbage collection, or is that come from a publication step? The latency is just the request latency, like how much time it takes a request to start and finish, like the time.
Yeah, so the most significant element that affect the latency is, so what is the most significant element?
I think it depends. If you go beyond to like P99 and or so, then it's the tail latency, because we force back to image, so it's GC contributes a lot. While in the P50 or P90 below, it's just the mutated time. Most of the time is spent in mutated.
Thank you.
Okay, thanks. Let's thank the speaker again. And the next talk is by Dan Pluking, Gul Agha, and Fabrizio Montesi. And Dan will give the talk.
Yeah, can you guys hear me in the back? Yes, thank you. So let's just jump into it. What are actors? Well, imagine you've got a distributed system. It's a little bit hard to see, but these are two nodes. And imagine you've got some kind of resource, like maybe it could be a container, it could be some large shared data structure, it could be a file, in this case it's a file. And maybe you have a couple of threads on node 1 that are trying to access that file. Maybe you even have a thread on the other node that's trying to access it. And you have a couple of issues in this situation, right? One is concurrency control. You need to make sure that the threads aren't writing to the file at the same time. You need to make sure there's some kind of way for that thread, thread 3, to be able to actually access the file even though it's on a different node. And you probably want to be able to clean up the file when you're done with it. So actors are just these lightweight processes that solve those three problems. You can think of it that way. So we take the resource and these threads and we put them in these little boxes called actors. And now, instead of those threads writing to the data structure to the file directly, they send a message to the actor who owns the file. This one wants to write, this one wants to read. And now also, you can give actor 3 a reference to actor A by just sending it a reference to that actor. And now it's able to also write to the file, even though it's on a different node. And eventually, some thread on node 1 is going to wake up, and it's going to check actor A's mailbox, and it's going to process those messages one at a time. So this kind of solves our concurrency and distribution issues. And there's lots of languages that have actors as a built-in abstraction. There's frameworks for every language under the sun, like Java. You've actually got a few ad hoc implementations of actors. If you look at the source code for these frameworks, you'll find that they've invented their own actors. That's kind of fun. Lots of different software that's made with actors. Now, the reason I'm telling you all this is because there's going to be a point in the talk where I'm going to be kind of like when your friend is explaining a really complicated board game to you, and after like an hour, you're like, I don't think I really want to play this board game anymore. Just remember this slide when that happens, okay? These are the people we're fighting for. So the situation we're trying to deal with is terminating actors at the right time is really hard. One of the situations we can have here is maybe a task. It's asking its manager if it's allowed to commit, and it's waiting for the manager, but then the manager doesn't reply. And maybe even the TCP connection closes. Now the task is wondering, what do I do? Do we just leave the task running, and then we're underutilizing our cluster, or do we go ahead and kill the task, and then maybe the manager comes back online, it sends a message, and we get some kind of software error. And if you're revisiting these slides later, you can see some real-world examples of this in Hadoop. It's kind of fun to look at. So the problem is basically you have to clean up these actors, you have to kill them, but you don't want to do it too early, you don't want to do it too late, and you somehow have to predict all possible failures that could ever happen, which is quite a task. So we'd like to have an actor garbage collector that detects when an actor is garbage. It doesn't kill any actors that could potentially receive a message, but at the same time, we want it to kill all the garbage actors. Like if a node crashes and I become garbage, you want to kill me. It was worded weird. And we want it to be simple enough that we can actually prove these two properties actually hold. And generally, we want this to be fast, by which I mean we don't want the actors to block when garbage collection is happening, and we don't want to add too much overhead to those actors either. So this is that slide that I warned you about. Like, we're going to get through this together. The point of this is just to tell you guys that actor garbage is fundamentally different from the garbage that you might be familiar with. So let's look at what that actually looks like. So here we have a busy actor. It's currently executing. And what can the actor do? It can maybe spawn some new actors. It can even spawn them onto remote nodes. You can send messages to an actor. See, when the chicken spawned the two chicks, it gained references to those actors. And now when you have a reference, you can send a message. The messages can also contain references, as I've mentioned. And then actors can also forget references. But notice that these references, they don't really function like channels. That message is still outgoing, even though the chicken doesn't have a reference to the gray bird anymore. So anyway, and now that chicken has finished processing that message, and it becomes idle. And when an actor is idle, it means I'm done working. I'm now just going to wait until I receive another message. So if you've been following along, can anybody tell me who is garbage in this scenario? No guesses? OK, it's the chicken. The chicken is the only one who's garbage. And here's why. So actors are fundamentally reactive, which means that they only process things, they only do computation when they receive a message. So if this chicken is idle right now, it's not doing anything. And it doesn't have any incoming messages, so that is a strong candidate. The other thing that you need to remember is that actors are capability secure, by which I mean that gray bird, it's not going to be able to gain a reference to the chicken because there's just nowhere for it to come from. So we can see now, hopefully, that there's no way for anybody to send a message to the chicken, and therefore the chicken is garbage. I should have really picked better emojis. So that one is garbage, and maybe some computation happens, and now we have the yellow bird and the gray bird, they have references to each other, and they're idle, they're waiting for messages. Who's garbage now? Call it out. Neither of them, actually. Because the gray bird, it's about to get a message. When that message is delivered, then it can do some computation. You don't want to kill him. And when he is doing computation, he has a reference to the yellow bird, so he could send it a message. So yellow bird isn't garbage either. So it turns out nobody's garbage in this scenario. But, what if that message got dropped? Now, or what if maybe this node crashed? Interesting question. Well, now look, the yellow bird, it's idle, it's waiting for messages, but nobody could possibly send it a message. So now actually everybody's garbage. So these are the interesting kinds of problems that you have to deal with. In general, I want you to kind of know that actor garbage, the way that we're defining it, it looks generally like those orange nodes. It's just clumps of circles, which is very different from traditional notion of garbage, which is like reachability from a root set. We don't really have a root set. What we're really interested in is, can an actor ever receive a message? So hopefully, if you take away one thing from my talk, it's that. So we have to do a new technique. Oh, and while I'm talking about actors, I might as well mention, I've been talking about detecting crashed nodes, but you might be wondering, how do we actually detect if a node is crashed, right? Because if I send a message to, well, if a node is not responsive, maybe it's just a network partition, maybe it'll come back. Well, in practice, actor frameworks like Apache Peko and Akka, they have this useful trick, which is if a node is slow for long enough, they just get kicked out from the cluster. And that's really useful from an application point of view, because it means that I can finally, if a node has indeed crashed, I can detect that it's crashed, and I can take some kind of action. And then I don't have to be afraid that actually it was just really slow, and it's going to come back, and I'm going to have to face the consequences of my actions. I don't want to face the consequences of my actions. So now getting into the actual garbage collector. There's really two challenges that we want to deal with. One is, of course, consistency. Here's a little example. Here's our chicken and chick again. Imagine that the chicken spawns this gray bird, it sends a reference, and then it becomes idle. And now let's say that we're kind of doing a naive garbage collector. It's just, actors are just going to send information about what they look like right now to the garbage collector, and we're going to see what happens. So the chicken says, well, garbage collector, I'm idle right now, and I have a reference to this yellow bird. That's all the information you know. And now the garbage collector has this view of the world that's starting to build up. Do I need a drink of water? Okay, whatever. I can't even find my water. So now imagine that the yellow bird, what's it going to do? It's currently executing. It might send a message. It might forget that reference, send another message, and go idle. And now it sends a message over to the garbage collector. And it says, I'm idle. I have a reference to the chicken. And now the garbage collector has this view of the world. Some conversation? So the garbage collector thinks, here are two circles that are pointing at each other. If you've learned anything from the past part of the talk, it's that clumps of circles are garbage. So the garbage collector thinks that these guys are garbage, and it's going to try and kill them, which is no good because, as you've learned, oh, thank you so much. I guess I really did need that water. That's really nice. So as you've learned, remember that gray bird, it can receive a message, and then it could potentially send a message to the chicken. And the chicken also has this incoming hi message. So none of these actors are garbage really right now. So we really don't want the garbage collector to kill them. So basically we have these two fundamental problems. One is to get a consistent view of the world from the garbage collector, you need to really carefully time when you send information to the garbage collector. Consistency is really paramount so you don't make mistakes. And the other issue is that we need to make sure that we get enough information from everybody so that we also don't make mistakes. Because if you remember from the previous slide, that garbage collector, it knew about the chicken, it knew about the chick, but it didn't know about the gray bird. And the gray bird, it made all the difference. So here's the key idea. One of the big ideas of this work is that instead of trying to time everything so that we're going to get consistency, we're going to add information to each actor's local state so that if something looks consistent, it turns out it is consistent. So to give you an analogy that I've been advised not to give, but I will give it, imagine like you're taking pictures of an elephant, right? You've got a picture of its legs, you've got a picture of its head, and you're looking at these two photographs and you're trying to decide, do these match up? Are they consistent? Were they taken at the same time? And just by looking at the photographs, you don't know. You have to make sure that the photographs are actually taken at the right time. But what we're doing instead is saying, instead of photographs, what if they were jigsaw pieces? And we have the guarantee that when you put jigsaw pieces together, if they fit, they are consistent. So that's the basic idea, is that we're going from photographs to jigsaw pieces. Or pretend I didn't say anything, if that made you more confused. So what we're doing in that same scenario is we're adding information that we're telling the garbage collector. So the chicken, instead of just saying, I'm idle and I have a reference to the chick, now it's saying, by the way, I also created this new actor. Now the garbage collector has a little bit more information. It knows about that gray bird. And when the chick sends information, it says not only that old information, but it also says, I sent a message and I also sent a reference. And so now the garbage collector merges all that information, and it still sees that the chicken and the chick have references to each other and they're idle, but now it knows that there's this unknown actor that I haven't heard about, and he has a reference to one of my actors. So now the garbage collector says, I'd better not collect this garbage because maybe that, I don't know what that gray bird is going to do. So that's good. It saved our problem that we had before. And now maybe that gray bird, it actually does get the message and then it immediately throws away the reference. And it tells the garbage collector. Now the garbage collector updates its information and it sees, okay, the chicken and the chick, they're two idle actors. They have reference to each other. They're garbage. Perfect. So we've solved our problem there. Whew. Okay, another drink of water. So I'll take a little cognitive break. Okay. The second, and there's only two challenges, don't worry, this is the second challenge. It's what do we do when nodes crash? So imagine now that our friends are all on different nodes, and we have this situation where the garbage collector knows information from the chicken and the chick, but it's waiting for information from the gray bird. But then, oh no, the node 1 crashes, or it gets kicked out of the cluster for some reason. And now the garbage collector is stuck. Because remember, we added information to each actor's local state so that we would make sure that the garbage collector could find out all the information. And now it'll never get that information that was on node 1. This is really terrible news. Specifically, the information that we wanted to get was, for example, how many messages did node 1 send before it crashed or before it was kicked out? So maybe it sent a message to the chicken, we don't know. Secondly, we'd like to know, well, the gray bird had a reference to the chicken, did it maybe send that reference to any other nodes? So maybe the reference leaked out to all these other nodes in the cluster. And now we're back in that old situation where it turns out we have to scan the entire cluster in order to just figure out, are there any messages left over? Are there any references left over? What do we do? So this is like a fundamental problem, right? How do we recover data that was on a crashed node that we need in order to perform garbage collection? This is the second trick. Instead of asking the crashed node, we just ask its neighbors. This, using another annoying analogy, imagine, if you want to get to know a person, you could ask the person what they're like, but you could also just ask their friends and family. Maybe they'll give you actually a more accurate picture of what that person was like. So that's the other big idea. So what we're going to do here is after node 1 crashed, we can't get the information from the gray bird, but what we can do is we can wait for node 2, and we can assume that each of these nodes, as messages are coming into the node, it's keeping track of what messages came in and who they were sent to. So node 2 says, I actually got one message, it was sent to the chicken, tells the garbage collector. Node 3 says, I didn't get anything. And these other 2 nodes, they say that we got references. So once the garbage collector gets information from all the remaining healthy nodes, it updates its view of the world, and it says, okay, well, actually the chicken doesn't look like it's garbage, because it has this message that's coming in, there's references to it. But look at the yellow bird. It turns out that the only actor that had a reference to the yellow bird has crashed. Its node has crashed. So it turns out that the yellow bird is crashed, and the garbage collector is able to figure that out. It's able to recover after the node crashed or was kicked out of the cluster. So those are the 2 big ideas. And let's talk about, get away from these birds and get into the machine. This is not a great figure, but it's so cool, and it's in the paper, and I know none of you are going to look at the paper, so I just wanted to show you. I love this figure. The basic idea of how this is going to work is that actors, they send updates to the garbage collector, but they can send updates whenever they want. You can customize this, actually. And the garbage collector, it merges that information from the left, and it builds a picture of the world, like I've talked about before, and that's called the shadow graph. The shadow graph represents its view of the world. And then the garbage collector, at any point in time, while it's merging that data into the shadow graph, it can then trace the shadow graph and figure out from that which of the actors are garbage retroactively. So that's collecting local garbage, and the way that we collect distributed garbage is that each local garbage collector on each node, they're exchanging information about updates that they got from their local actors and messages that they got that have entered the node. They're exchanging that information with each other so that every local garbage collector has an eventually consistent view of the entire cluster. And the remote garbage collectors, in addition to merging everything into their shadow graph, they also build these things called undo logs. And the undo log is basically like a in case of emergency break glass. This is what you do when node X fails. So if node X gets kicked out of the cluster, I'm going to take the undo log for node X, and I'm going to merge it into the shadow graph, and that repairs the shadow graph. And I really regret using the word undo log because it kind of implies that it grows monotonically, but actually it doesn't. It's actually, I expect it to be quite small in practice. We can talk about that a little bit more later. You can get the numbers from the paper. The important part is that I need your help. This was just, this work has been a kind of a proof that we really could do realistic distributed garbage collection in actor systems. But this is just the first step. There's a lot that needs to be done to actually make this really practical, that make it fit for human consumption. So for example, I haven't tuned really that local garbage collector at all. Things like generational garbage collection, things like how often do actors send messages to the garbage collector. This is unexplored territory, and I think there's interesting points there, basically. And I have a lot more to say about every single one of these things, but I'm running out of time. Another issue is that the actor framework where we implemented this, it's called Apache Pecco, it's a library for Java. And so our garbage collector, it's also a library for Java. And the garbage collector somehow needs to know the references that you're passing around. So right now, we just have to manually tell the garbage collector, I'm sending this reference to this person. So it'd be really great if we had maybe like a static type, some kind of type system, some kind of static analysis that would prevent the user from making mistakes, forgetting to notify the garbage collector about something. I'm about out of time, so talk to me about other things like this. Thank you for listening to my talk, and I would be remiss if I didn't mention I'm on the job market. Thank you.
Thank you very
Thank you very much. Do we have questions? Please state your name.
Hi, this is someone from NYU. Could you go back to slide, I think it was 39. Here, so I'm curious how you get, what happens in a trace where you ask all its neighbors, hey, what did you receive from the pigeon? But say like the chicken haven't received a message. Like the message sent from the pigeon to the chicken hasn't arrived yet, so the chicken says, I didn't receive anything from the pigeon yet.
Oh, and then it arrives after it's reported that information? So the way that that works is when a node gets kicked out of the cluster, you make a promise that you're never going to receive any more messages from that node if they arrive.
Got it.
Yeah.
Okay, thank you.
Hi, thanks for the great talk. Leonard from University of Montreal. I was wondering, it seems like you send a lot of message to the garbage collector. Do you know a bit what the overhead of doing this is?
Yeah, it's really hard to measure. The idea is you can tune it is the thing. Basically, there's kind of a trade-off between how much information each actor stores locally and how often I send messages to the garbage collector. So I give them each a fixed size local memory, and when your memory fills up, you send a message to the garbage collector, and you also send a message to the garbage collector whenever your mailbox becomes empty. But you can kind of customize that sort of thing. Aside from that, there's no messages that we add between the actors. So we actually have an improvement over garbage collectors like the Pony garbage collector, and because we don't have way to reference counting and our interactions with the garbage collector, there's actually less messages. But yeah, it's really hard to give you a concrete answer on that. It can be tuned, basically.
Hi, Steve Blackburn, Google, and Australian National University. Great talk, I really enjoyed that. What I was trying to do, being a GC person, was map this onto my mental model of how GCs worked, including work I did decades ago on distributed GC, where there's seems to be a lot in common. One thing that struck me is that you said really early on something about mark sweep's not applicable because these messages are in flight and blah, blah, blah. It just seems to me that one way to model that is to think of those things as routes. Mm-hmm. Like so in a normal runtime, you've got all sorts of mysterious stuff happening in the compiler with register spills or whatever else, but we just consider those things to be routes. And as long as the runtime has some mechanism for reporting that to us, then the complexity of that is less relevant, as long as it can guarantee that it can report what those routes are. And I'm just thinking of the actual messages and all the rest of it. If you can model those things as routes with respect to each one of those, that might just be one way to think about it, which takes it closer to classic GC algorithms and so on. Mm-hmm. And the other thing I was just thinking about is how this maps onto classic distributed GC algorithms. That was more of a comment, maybe a question. I'm not sure, but I enjoyed the talk, and I'm kind of interested in mapping this onto some of the old school GC stuff.
Yeah, that's two great points. The first point is I didn't get a chance to really talk about all the incredible related work that there's been. There's actually been, it's a paper called the pseudo-root approach from Wang and Varela, and they did exactly use kind of this idea of an actor that has messages in its mailbox is a pseudo-root, and we can treat it that way. And that works really well, but their particular garbage collector, it adds a lot of messages, and it doesn't recover from when a node crashes. It can just kind of move on and make some progress while that happens. I've been told that those kind of shared memory tricks add issues with cache coherence. I don't really understand. I'm not like a traditional GC guy, so I would love to talk to experts like you in that space to find out. I also wonder exactly how these things map to one another. I hope that there's some kind of insight that we're not just parroting something that somebody did in 1990. Of course, that's all we're doing, really. But yeah, thank you for your question.
Hello, I'm Kunshan Wang from Australian National University. I'm working on the Ruby programming language, and some programming languages, including Python, Ruby has some notion of coroutines in different form, and Python has generators, and Ruby has fibers. And it's possible to implement actor model using those fibers and generators, but more often than not, in traditional use cases in those languages, they were used as some kind of iterator or coroutines. The difference between that and actor is that they can't execute autonomously, but they are explicitly suspended or resumed where there's only one thread of control swapping between different jumping between coroutines. So I think that the idea of determining which nodal actor is live is helpful. And though, of course, in those languages, the fibers and generator also need to be garbage collected. So can some of your thoughts be generalized or specialized, if you prefer, to the coroutines rather than actors?
Yeah, I really should have, in that slide where I had all the actor stuff, there was out over here where you couldn't see, there was all the coroutine stuff that technically kind of counts as an actor. But I'm not really familiar with coroutines, so I don't know how well those processes would map to each other. But maybe if that's like a garbage collection problem, I don't know if the distributed coroutines are a thing that could be?
No, yeah? It is just one machine, one thread.
Yeah, okay. Maybe there could still be an interesting work there, but I wouldn't know. We could talk about it after.
Thank you.
Thanks so much for your question.
Okay, let's thank the speaker again. And get the next speaker. So our next talk and the last talk in this session is by Mohammad Amit Hassan Arovi and Ruslan Nikolaev from Penn State. And Mohammad will give the talk.
Hello, everyone. I am Mohammad Amit Hassan Arovi from the Pennsylvania State University, and my today's talk is RRR SMR, Reduce, Reuse, Recycle, Better Methods for Practical Log-Free Data Structures. And this work has jointly been done with Dr. Ruslan Nikolaev, also from Penn State. So to begin, modern systems have multiple cores and need efficient resource management for better performance. So for this purpose, log-free data structures are becoming more popular as they avoid deadlocks, improve scalability, and ensure system-wide progress. However, log-free data structures are quite difficult to use. In particular, it's not easy to move objects from one data structure to another. In this talk, I'll describe the problems that arise in this context and also present our solution regarding how we can actually move one object from another one data structure to another with copy-free manner. First of all, let's consider an operating system scenario where we can have multiple lists. For example, let's say we have two lists where we have tasks ready to be executed and another list where we have tasks waiting for I/O. Now what we want is that we want to move G from the task waiting for I/O to the list ready to be executed. In trivial log-free data structures, memory reclamation needs to be safely handled. For example, here, if a thread deletes the object F from the list and another thread has still dereferenced to it, then the second thread can easily crash if the first thread has already reclaimed the memory. So therefore, we have to make sure that we do not prematurely reclaim any memory, and these can easily be done with well-known memory reclamation schemes such as epoch-based reclamation, EVR, and hazard pointers. But this problem is not very unique. What is unique in our case is that how we can move objects directly from one list to another without involving the memory reclamation scheme. But we can actually work around this problem by allocating new object and copying, but this will come with copying overheads and sometimes infeasible in terms of interrupt context. So now before I go to the solution that we propose for movement of objects from one list to another in copy-weave manner, let's take a look at a very classical data structures called traverse stack. In traverse stack, we have a top pointer which points to the top of the stack, and we use an atomic hardware primitive called compare and swap to change the top pointer to any node of the stack when we perform insert and remove. Cache basically what it does is it checks a shared memory object to an expected value, and if the matches, it just changes it to a new value. Now, the question is, can we directly move objects from one stack to another before we move to the more complex data structures? So before I answer that question, let's see a very trivial and common problem in concurrent systems, which is called the ABA problem. For example, suppose we have a traverse stack with A and B as a node, and the top pointer is currently pointing to A. Now thread 1 begins its operation, and it wants to remove A from the stack. And before it does a successful cache, it gets preempted, and now thread 2 comes into the action. Now thread 2 sees that, okay, fine, I have the list, and it's still pointing to A because we didn't change the pointer top to B previously with a cache. Now it removes A, successfully do a cache, points to the B, and then it pushes C again, and then it pushes A, reusing the same memory address. Now all on a sudden, thread 1 resumes, and it says that, okay, fine, we have still A in the stack top. So let me actually do the successful cache, and it now points to B while it leaves C hanging. Now the question is, what is the solution for this? So for this, we can simply have a monotonically increased stack adjacent to a pointer, and then we can just do a white cache, which is in x86 64, it is known as compare and exchange 16 byte. So now the question is, okay, we can go back and say that, okay, is it possible to move things around in stack? Yes, it is if you take care of the ABA problem. But what if there is more complex data structures such as Harris lock-free linked list? So here in Harris lock-free linked list, we can remove nodes arbitrarily from anywhere of the list. It's not the top of that stack anymore. That's you need to just take care of the top, not like that. So here you can remove any node from anywhere, and concurrent deletion can take place and can remove adjacent nodes. So before I move into that, I just want to have a remark. When Harris list actually shows that there are two-phase deletion needs to be taken care of here. He says that in his research is that we have to first make a node logically deleted, and then we can subsequently physically unlink it from the list. So why we need that actually? Why we need logical deletion and physical unlink? Because you could have concurrent threads that are removing nodes from anywhere of the list, and to make sure that those deletion are safe, you need those notion of logical deletion and physical unlink. So now we come to the main part, is that for our RRR safe linked list, what are there, we need to make sure that we can recycle nodes without involving the SMR schemes. So we need to make sure three things here. The first thing is that we have to make sure the ABA safety. Then the second one is strict ownership. And the third one is safe traversal. Now for the problem 1 solution, we still have the monotonically increased stack adjacent to a pointer, but unlike the traverse stack, we have to make sure that here, before proceeding to B and we read the B tag, we have to read its predecessors A tag, and then we can do B tag and A tag. That means we have to make sure a sandwich-like facility is here. And that's how we solve our ABA problem here. from the second solution of the strong ownership model, what we need to do is that, for example, if we are deleting B from this list, we have to make sure that the thread that is logically removing the node owns it, because as soon as you are done with the remove operation, you have to make sure that you have the node, because some other threads, you cannot let some other threads take it. So for that, we have to do successful physically unlink, but there is a catch here, is that what if even before you recycle the node, some other threads insert something into the node before B? That means the cache will fail. Then how we make sure that we have got the node? In our paper, we introduce a special search operation which will search for that particular node when the cache fails. So if the cache fails, there could be two scenarios. That means some other thread has already removed it from the linked list, then we are fine, that's good. But what if it's still there? That means that the state of the list has been changed. So then we do that special search operation, and we look for that pointer, and then we unlink it, and then we can just recycle it. For problem 3 solution here, before I go into the solution, I need to have an example here. Suppose you have a list with A, B, C, D, and now concurrent remove operations logically delete B and C. Now it does a successful cache and physically unlink B and C. This scenario is totally okay for epoch-based reclamation, but it is not okay for hazard pointers. For hazard pointers, what we need is a so-called Michael's modification. So whenever we have some logically deleted node, immediately we will try to unlink it from the list. So this Michael's-like modification is needed for our scope of work. It is not only needed for the HP, but also for EBR. Why it is that for EBR? Here we can say that B is physically unlinked here. So my question is why you need that for EBR, even if it is for HP, it is okay, understandable. For example, to answer that question, I need to have an example, is that you have a list 1 with A, B, C, and then B and C subsequently adjacent nodes that are deleted. Then even before you recycle B, some other threads come and recycle C. Then when you traverse the list 1, you may end up in some other list. So that is why we need to make sure that we have Michael's-like modification in our case for both HP and EBR. Now, in addition to linked list, we also show a binary search tree, recyclable binary search tree, which is called Natarajan-Mittal tree. So in Natarajan-Mittal tree, leaf nodes actually contains the primary keys, and the internal nodes are used just to traverse. But in Natarajan-Mittal tree, we have the internal node and the leaf node, but whenever it is getting inserted into the any node that gets inserted into the binary tree here, it comes with an internal node and the leaf node itself. And when you remove it, you have to take care of both the parent and the leaf node. So that is a problem. So for Natarajan-Mittal tree, you have to make sure that we still have the solution, 3 solutions that we described in the list, but now we have to take care of one special scenario. That is what if you have 2 concurrent removal operation here, that means D and E will be gone. Then who is going to take the parent? So that's a confusing situation here. Because when you recycle, you need to recycle both the parent and the leaf node. So for that, we propose a solution where we do not have the information directly into the pointer of the internal node for the leaf node. We do the solution through an indirection, through a block. So where we put all the information for the leaf nodes, and the pointer has also a tag, and that pointer in the internal node points to that block. So now the pointer has left flag and right flag, the lower 2 bits, just to make sure that simultaneous deletion is not happening. And then if you want to move now D from here, you first set the L flag and then when you remove it from the Natarajan-Mittal tree and want to recycle both the parents C and D, you need to take the sibling E and attach it to the previous position of the parent, and we do that through a spare per thread block because our block is immutable. As we are attaching E to the A again, we just swap per thread spare block, we initialize the value, and we just swap it and point to the next block to be used again by the thread if needed. In addition to linked list and Natarajan-Mittal tree, we also shows a performance for memory overhead reduction for Michael and Scott queue here. As we know that for Michael and Scott queue, we have tag and pointer for every internal nodes, and we need white cache for all of them. But to reduce the memory overhead, we started that we just need to keep the tag to the last node instead of the pointer, and the head and tail can only have the white cache because it has the tag and pointer, and that's how we can actually reduce some memory overhead here, and details has been described in the paper. Now let us see the evaluation setup. For evaluation, we used 128-core AMD server with SMR schemes, epoch-based reclamation, and hazard pointers, and the benchmarks include queue, linked list, and tree variants, where we measured both throughput and memory waste. By memory waste, we refer to the not yet reclaimed memories, and we use payloads of 128-byte and 64 kilobyte for the data structures. Now, in the evaluation, we have the recycling percentage of 50% and 90%. So what do I mean by recycling? Is that 50% of the time, if I say that 50% recycle, that means 50% of the time you move one object from one data structure to another. But as the baseline doesn't facilitate the move operation, we emulate it through insert and remove and reallocating and copying the data. But for our modified version, this 50% recycle means we just directly move objects from one data structure to another. So here we show that for evaluation linked list throughput, we are showing 128-byte payload and 64 kilobyte payload for both 90% recycle. And our modified version of the algorithm outperform the baseline for both of the HP and EBR reclamation schemes. And also we see the similar trend for 50% recycle scenario for 128-byte and 64 kilobyte payload for linked list. And for Natarajan-Mittal tree, we observed that for 90% recycle in 64 kilobyte payload, we almost achieve like 10 times performance benefit than the baseline one. So our code is available here in this repository, and thank you so much to attend the talk.
Thank you. Any questions? So, yeah, come to the mic and please state your name.
Hi, Sungwon from NYU. I'm curious, so this recycling is kind of something that is new, that it's one of your contributions from the paper, so I assume that not many code bases actually consider this, or probably haven't considered this when they were building their code base, meaning that their workload is going to be 100% not recycling.
Like allocating, right?
Yes, exactly.
Yes, yeah.
In that case, how does yours compare to, in 100% like non-recycled workload, how does yours compare to existing solutions that?
Oh, so we showed the 90%, right? So you mean by 0%?
Yeah. If
no recycle, right?
No recycle.
So in no recycle, we have, we didn't actually see no recycle, but we have in the paper of different recycling percentage, like what we have in 10%, because our work is not like 0%, because that's not the notion of the work. So you need at least some recycled percentage. That means to the lowest point, we have 10% in the paper, because we cannot just show everything here, but we have in the paper is that 10%, 20%, 30%, up to 40%, and then we show 50 and 90, so it shows the similar trend.
Awesome. Looking forward to reading the paper.
Yeah, yeah, sure. Thank you for the question.
Hello, my name is Jung Young Kim from KAIST, and it is quite interesting to me because I think it has both similarities and difference to version-based reclamation, because both version-based VVR and your scheme use timestamping with double word atomic operation, I guess. So, but at the same time, your scheme seems to support reclaiming the node if you want, right? So, so did you compare VVR and your scheme in your?
Oh no,
in your work?
we just compared EBR and HP.
I see. So then have you considered? I mean, what do you think about the difference between your scheme and VVR?
So I think that when you have EBR, you can have the highest performance, right? And if you have HP, you have robustness.
Yeah, right.
Then VBR doesn't actually basically come in between those if you need some trade-offs, right?
Yeah.
So that is why we just focused on if you need some performance, you go for EBR, and if you need to have robustness, you go to HP. So that is why we had just EBR and HP. But I'm not super sure about what will happen for VBR.
I see.
Yeah.
Thank you. Yeah.
Yeah, sure.
Yeah, maybe I would just say VBR lets you like reclaim without waiting, and then you check if you touch and reclaim the object. So it is a nice idea to try and check how it relates. Yeah. Okay, that concludes the session, and we have lunch
Thank you
now.
so much.
Thank you very much.
Thank you so much.
So thank you so much for coming to the session on concurrency. Obviously, all of you are going to be interested in concurrency. The first talk is about efficient timestamping for sampling-based race detection by Minjun. Please welcome our speaker with a big hand.
Hello, good afternoon, everyone. My name is Min Jian. I'm from the University of Illinois at Barnard-Champaign. Just talk. Can everybody hear me? Okay, so this is a joint work with my dear collaborators Daniel Lim and Uma Mathur from the National University of Singapore and Mozart and Mahesh from UIUC. The talk will be about some algorithmic improvement on dynamic risk detection under a specific context called sampling. Okay, so let's start with data race. The data race is a pair of concurrent accesses to shared memory without proper synchronization. It is a crucial concept in concurrency testing, given that many modern compiler optimizations and memory models assumes or requires data race freedom for its correctness. For instance, data race is an undefined behavior in C11, which means that the compiler can make whatever assumption it wants to make to the instruction that causes a race, including that instruction does not even exist. And another example will be Java, which usually requires data race freedom for the program to behave in a sequential consistent manner. So one way to test data race is dynamic analysis, which in some sense focus on the monitoring program that for a given concrete execution, it detects whether this given execution has a data race. Dynamic analysis is typically sound, and by sound in testing, we mean that whenever the approach says the execution is buggy, it must be buggy, okay? But it can still miss bugs because it only checks for one execution. It does not explore the full interleavings. Dynamic analysis typically is completely automated, and therefore it is widely adopted. So there have been several widely adopted tools that does dynamic analysis on races, with thread sanitizer being one of the most prominent. But the base logic behind these tools is a classic algorithm called the vector clock algorithm, which detects races by sort of capturing the causality between events via vector timestamps. This algorithm runs in time theta n times t, where n is the number of events and t is the number of threads. Monitoring a program with this vector clock algorithm can result in a very huge overhead. And I'm pasting the disclaimer from Tsan's official website, which is basically saying that running your code with Tsan can make it very slow. Okay? So one of the popular ways to mitigate this overhead is sampling. And the rough idea of sampling is that you only do risk detection on a small set of events. And the high-level intuition is that meaningful behavior information of the program can often be extracted without analyzing every event into full detail. So sampling-based risk detection, again, they are still typically sound, namely we do not tolerate any false alarms, and they have much lower overhead comparing to the other case. And they detect the races with some probabilistic guarantee, depending on how the events are getting sampled. So given these advantages, it's not surprising there has been an extensive research on this topic. And sampling-based risk detection centered around two key questions. The first one asks, how do I pick the samples? Or specifically, which memory access events should we sample in order to increase the likelihood of detecting races? And the second question asks, like, once this set is determined, how do we check for races? And the the majority of the period research has primarily focused on the first question. They proposed many efficient strategies, including random sampling or combined with static analysis to identify the instructions and memory locations that are more likely to be buggy, or even rely on user-guided information. However, the second question, namely how do we check for races once this set is determined, received far less attention. Although many of the prior research had attempted to address the second question with some heuristics and optimizations, they lack an algorithmic foundation, and the common fallback remains to be running the vector clock algorithm, but ignore all the events that were not sampled. And in the worst case, this naive approach have the same running time complexity as the case without sampling. So this leaves a very interesting open problem that if we can design an algorithm that symptomatically beat this naive approach. Okay, so in our so this is a major focus of our paper, and in our paper we formulate this problem, namely the second question, as a marked analysis problem, which basically asks that for a given execution with S marked event, and determine if any of the two marked events are in race. And here I'm providing a summary of our result compared to this naive algorithm I just mentioned. So both of our algorithm and this naive algorithm runs in a one-path streaming manner, and they are both sound. Again, by sound we mean that we do not report any false alarms. And for the running time, the naive algorithm is the same as running the vector clock algorithm without sampling. It runs in time theta n times t. And our algorithm runs in time of OST squared, where S is the number of marked events. Okay? And both of the algorithms can be efficiently parallelizable. At the end, it's sort of worth mentioning that the algorithm we proposed will output exactly the same as races as this naive approach. Here we also show some highlights of the evaluation, and we show that when the set S is relatively small, like 0.3% comparing to the size of the execution, our algorithm can reduce around 37% of the overhead introduced by the naive approach, and up to 70% on some benchmarks. And it's sort of important to notice that the naive algorithm also benefits from sampling, because it also ignores the 99.7% of events that are not sampled. And with a relatively larger sampling rate, like 3%, our algorithm still reduces around 20% of the overhead and up to 37% on some benchmarks. Okay, so let's now get into some technical thing. Let's firstly give a definition on data arrays. So for a given concurrent execution, we firstly consider two partial orders. The first one is intra-thread ordering, which is just a total order on the events of the same thread. And the second order is a total order on the accesses on the same lock, which means we assume sequential consistent behaviors on lock accesses. And the happens before relation is the smallest transitive closure of these two partial orders. And we see that two accesses form a race if they are not ordered by happens before and they access the same memory location, and at least one of them is a write. Okay, so the vector clock algorithm works in the way by assigning every event a timestamp. The timestamp stores the knowledge of the event about how many events happens before this particular event E from each thread. In some sense, it's like the number of events E knows. And it's kind of intuitive that this timestamp can be used to capture the happens before relation between two events, because let's say E1 happens before E2 if and only if every event E1 knows is also known to E2. Okay, and the vector clock algorithm operates in a very classic way, like a message passing algorithm, in the sense that each thread is maintaining its own local information, and they communicate this information via log accesses, namely like release and acquires. More specifically, what we can think the release is the sender of the message, and the acquire is the receiver of the message. But this communication is not free. It is achieved by vector clock operations. Intuitively, when I receive an information, I would like to learn from the information I received. So the vector clock data structure supports this operation called the join, which takes two vector clocks and returns the pointwise maximum. And when I send the information, I would like the log to carry my knowledge. So I just wanted to copy whatever I have. So the vector clock also supports this copy operation. And both of these operations runs in time all of t. So that is why the total overhead of the vector clock algorithm remains to be theta n times t. And this is also why the naive approach, even when we are ignoring a lot of memory accessing events, still remains to be n times t. That is, we cannot omit these communications in order to be sound. So our algorithm is built upon this vector clock algorithm, but we have three observations that allows us to achieve this better running time complexity. So the first observation is that we can simplify the local timestamp so that there is a bound on the number of updates each thread needs to update its local information. When the number of communication is far more than the number of local updates, many of them just become redundant. So our second observation says that if we can avoid these redundant communications via something called the freshness timestamp. And finally, we also notice that even when a communication cannot be fully avoided, we can avoid it partially if we enhance the vector clock data structure with some ordering information. And the major contribution of our paper is a formal analysis on how to combine and apply these optimizations so that we can achieve a better running time complexity. Okay. So the sampling timestamp basically says that we can simplify the original timestamp by only remembering the number of marked events that event E knows. And this basically naturally bound the local information the thread, a thread kept can be updated. It is bound by S. And it's sort of very intuitive that this timestamp is sufficient to capture the HB relation between two marked events. And the second observation we made is that there is this freshness timestamp, which is like the knowledge of knowledge. What I mean by that is it stores like how many times the knowledge of another thread has been updated that is known to me. This in some sense tells us the freshness of the information. And the high-level intuition is that if I receive an information that in some sense is not fresh to me, I know everything, then I know everything this information is trying to deliver. I can safely ignore it. So a coarse example will be, you see for the execution on the left, if a thread T2 receives the information from T1 that has been updated for 10 times in the first communication, then it can ignore the second communication because it delivers the same message. However, on the execution on the right, if the second communication delivers a message that has been updated 11 times, then I cannot skip it. But it's sort of important to notice that I already know most of the information that is being passed in the second communication. And more specifically, there is only one update that I'm not aware of. So if I can somehow identify which entry it is, I can just look into that entry without looking into the rest of the entries. So the way we achieve this is by enhancing the vector clock algorithm with the ordering information. In some sense, now the vector clock, we associate the vector clock with two arrays that stores the information of how the order of the entries that gets updated. And now this special data structure supports a different kinds of join that takes in two parameters. Namely, one is another ordered vector clock, and the second one is an integer k, which basically says I just want to read the last k entries that this vector clock got updated. So in this previous case, all I need to do is just to run this join operator with k equals to 1, because I just want to know the last entry that got updated. And I'm aware of all other things, all other updates already. Okay, and finally, the last piece of this running time, of the improvement in the running time is to apply this shallow copy idea, which is sort of quite common in the context of sampling. And the rough idea is that because we can shift the cost of delivering the message into the case when you have to update your local information. Because when you have to update your local information and the information is shared among different delivers, you have to create a new deep copy. But because we showed that this update it can only happen for S times, it also naturally bound the number of deep copies we have to create because we're using this shallow copy idea. And for the experiment, we implement our tool upon thread sanitizer, and we run the algorithm on a system with 64 threads. We tested against the bench-based benchmark framework with random sampling. Namely, we randomly decide the side S in our formulation. And this is, we achieved some sort of, a visible reduction in the overhead, as I have already mentioned, but we believe this overhead can be reduced much more if we are able to optimize the implementation. And we also did some profiling during the experiment. We show that with the second observation, namely this freshness timestamp, we can effectively skip 50% to 70% of the communications. And now equipped with the last observation, this ordered vector clock data structure, in average, we traverse 3 to 6 entries per communication, while the number of threads remains to be 64. Okay, and for future work, I believe there is a dire need to improve our implementation for better evaluation of the algorithmic improvement. And it's also very interesting to see how this algorithm works with other sampling strategies, like the ones being guided by user information or static analysis. And it's also interesting to see if we can extend the ideas into other settings where communications happen to be dominating. And finally, we would like to know if we can further improve the running time complexity from S times t squared to S times t. Okay, thank you.
Before starting the Q&A, if you are the speaker for the second talk, please confront the second speaker. Okay, okay. Yeah, and if you have any questions, we will have time for a quick one question. Okay, let me ask a question. So sampling-based approaches immediately have a false negative, right?
You mean false negative? Do you mean I report a risk, but it's not a risk?
In reporting, yeah, right.
Yeah, so that is not in our setting. You never sample synchronizations. So that is why that is how we ensure soundness. It's more like you just ignore some memory accessing events, but you never sample synchronizations because you want your algorithm to be sound.
Okay.
And the whole idea is about how to play with these synchronizations. Yeah.
Okay. So you're the author, right? Okay.
So I'm just wondering, you mentioned the ordered vector clock timestamp. Is it possible to use like vectorization to boost the performance of this data structure?
Yeah, that's a very good question. We were not able to do it, and that was one of the reasons we don't see the running time improvement we were expecting.
Okay, thank the speaker.
Sorry.
So it leads to our second talk, which is about efficient linearizability monitoring.
Let's see here. Everything works as it should. Right, I need to plug it in. It might help.
And in the meantime, if you're a speaker for the next talk, please confront and talk to the student volunteers. And Samuel is going to present this work. Let's give him a big clap.
Okay, so thanks for the introduction. So this is joint work with me and my supervisors, Parosh and Bengt, and the two people from IIT Bombay, Krishna and Om. So I'm just going to move my mouse cursor because that's going to irritate me. Okay. So you have a concurrent system, and oftentimes they communicate through some shared object. And this shared object is, for instance, a stack or a queue or something like that. And this, to reason about the correctness of such a system, we need a correctness condition that's hopefully composable and that captures this interacting with a common object. And once the standard such correctness condition is linearizability. And linearizability is a way to extend a sequential specification, like the ones for stacks or queues, for instance, to a specification in the concurrent setting. And it does so by taking an execution. So this is an execution. We have operations that are these pushes and pops, and we have their calls is the left point of these lines, and the returns are the right points. So linearizability says, well, this history is considered linearizable if we can pick a time point in each of these operations, or alternative, extend the partial order that happens before order into a total order, such that this now sequential history corresponds to the definition of, or to the specification of the original sequential structure. So this is a stack execution, so the original history was linearizable. And we are specifically looking at the monitoring problem, which is when we take an execution like this and ask, is this linearizable? We're not looking at implementations. So we just expect a sequence of calls and returns to these operations. And unfortunately, this is NP-complete in the most general case, and even for simple structures such as registers. So we have to make some additional assumptions. And a common such assumption is that the histories are differentiated. And this means that each value just occurs in, at most, one adding operation, so a push, and removing operations, a pop. And in fact, this is a very sound assumption, because it turns out that for implementations, if you have an implementation that implements a stack, it is correct, like it's linearizable, all its executions are linearizable, if and only if all of its differentiated executions are linearizable. So it suffices to just look at this. So, and the second, well, rather this is a non-differentiated history. And the reason that we can do this is that this history, this non-differentiated history, is linearizable if and only if there is some differentiated history that we can obtain by just renaming it, or rather we can obtain the original history by renaming the values of this differentiated history. Okay, But this is a tricky problem, apparently, because this is linearizable. We just saw that on the first slide, but this is not. We only swapped the order of 2 events. So it's not always easy to see whether it's linearizable or not. And in fact, this has shown in previous work. So we have, in our paper, we have found errors in previous work, notably this is a quite recent paper on this that produced a quadratic time algorithm for monitoring stacks, which is incorrect. It does not differentiate between the 2 histories on the previous slides. And there was an attempt earlier in 2018 for an algorithm for something that is more general for a class of structures, which also was incorrect because you found a bug in the proof. The algorithm we don't know, but the proof was not correct. So we'll present our algorithms that we have proven are correct. And for stacks, it's quadratic in the length of the history. And we do this by computing what we refer to as populated and deserted segments of this of the stack history. And then we apply some simplification steps, which is either we remove extreme values or we partition it. I'll get to this. And if we ever cannot progress, we conclude that it's not linearizable. Okay. So the first thing is that we can ignore the threads. So here we have 3 threads that are performing operations, but the specification itself says nothing about the threads. It just cares about when things call and return. So we're just going to draw it slightly differently and just put the values side by side. Okay. So the first thing we do is we compute what we refer to as the cover. So between the return of the push for any value and the call of the pop for that value, we know that that value must be in the stack. Okay? So what does that mean for when we take the union of these? Well, that means that in this yellow, which we call the populated segment, which is the union of these covers, there must be at least 1 value in the stack. Okay? And in these green regions on the sides, we know that the stack may be empty because everything that's already been pushed has also had its pop called. Okay? So what do we do? Well, we start by finding extremes. So we see here that the push to B intersects the leftmost deserted segment, and the pop to B intersects the rightmost deserted segment. So we can just put B at the ends. Push B first and pop B last, okay? And then we start again. We compute the cover, we compute the populated and deserted segments, and this time there's no extreme value. So what we do instead is that we see here that in this middle, we have an inner deserted segment. And this means that there is some values whose pushes happen before this, the populated segment to the left of it, and whose pops are called at least here at the start of this deserted segment. And similarly, there is a populated segment here, so that we know there must be something to the right. So what we do is we just separate the history here. We say that, okay, well, we do whatever we want to do with the left side, which is A, and then we do whatever we want to do with the right side, which is C and D. Okay. So we look at the left first. Well, we do the same thing. This is maybe a bit easier example, but because we can just, it's extreme, we put it like this. And then we move on to the right side. We find the cover, we find the populated and deserted segments, we find that they are extreme, and we put them like this. We have found the linearization, hooray, the history was linearizable. Great. Well, we made some additional assumption. The first is that we assume that every history is completed, like every push has a matching pop. But if there are some pushes that do not have matching pops, we can just add concurrent pops at the end for those values, because we know that they will be in the stack at the end, because they're not removed. And the second thing is that pop operations might return, well, nothing, indicating that the stack is empty. And in such a case, we can just start like this. We can compute these again. And all of these that intersect a deserted segment, we can just remove them, because we know that the stack can be empty there, so remove it. Well, we still have one left, so this is not linearizable. Okay. Well, and the complexity, just to go through it, it's we sort the values, we compute the deserted and the populated segments in linear time, we find the extreme In linear time, we partition in linear time, and then in the worst case, each of these steps that we perform just removes one value. So n steps, computation, n squared. So, queues. Here we do a bit better. We do n log n, and we do this by exploiting a small model property, which is that a differentiated and completed queue history is linearizable if and only if, for no values a and b, we have that a is enqueued before b and b is dequeued before a. So we can just look at what we call critical pairs. So, yeah. And it is important to note that this does not hold for stacks. We can not use any property like this for stacks. In fact, in our paper, we show that we have a construction for a counterexample to there being a small modular property of size n for any natural number n. Okay, so what do we do? Or rather, this, we look at this small modular property expression here, and we compare this to these lines. So what does it mean? Well, it means just that the entirety of the operations for B, from its push call to its, or enqueue call to its dequeue return, is contained within the inner, or the cover interval for some other value A. Okay, so we just need to check containment for these intervals, and that we can do by constructing a tree. So we're going to construct what we refer to as a Q tree, and then scan it for the containments. So the Q tree is a red-black tree that contains a left and right subtree. It contains left and right endpoints for the inner interval, so it contains the inner interval for every value. And then it contains a high key just to help, which is the highest right endpoint occurring in subtrees, just to help us do the search without branching. Okay, so here's a big history. These are its inner segments. So here we have, for the value 0, we have its enqueue returns at 3, its dequeue starts at 6, so we have the inner segment 3 to 6. Okay, and the outer segments for 0, the enqueue starts at 1, the dequeue ends at 8, so the outer is 1 to 8. Okay, so we're just going to go through one of these containment checks. So we're going to ask if this outer segment, 1523, is contained in something else. So we start at the top. Well, 15 is less than 16, so we should probably go left. Okay, here we see that, okay, it's not contained in this interval. 15 to 23 is not contained in 9 to 14, okay. So we look to the left first and see that the high key in the left subtree is not big enough to contain wherever we go here, this high key is going to be too small. So we just proceed to the right instead and find this interval, and we have containment, so the history was not linearizable. And again, go through the complexity. Constructing the tree is n log n. Each search is log n, and we do n searches, so it's n log n. Okay, and finally, the simplest of the three is a multi-set algorithm. This is in linear time, and we do this by simply first stating that a multi-set history, or set history, is linearizable if every single valued projection is linearizable. So if we can just look at one value at a time, and essentially arrive counters. And then one of these single valued histories is linearizable if and only if the number of returned removes never exceeds the number of called adds. So we can just count, and we're done. Okay? And then there are some other operations you might want to be able to do on sets, for instance, containment checks, main membership queries, and we present in the paper we have a greedy algorithm for handling those. So, in conclusion, we have some monitoring algorithms for stacks, queues, and sets. And we have found issues in previous work, and yeah, we have shown that these are correct. So, for future work, I want to formalize this in a theorem prover. It's sort of work in progress on the side, just to be absolutely sure there is no mistake anywhere. And then to extend this to other structures, such as snapshots or other concurrent objects. And then finally extend it to related correctness conditions. For instance, durable linearizability. There is also k-linearizability and other similar properties. Okay. And thanks for listening. And I am finishing up my PhD and I'm looking for work. Hello, come talk to me.
Any questions?
So can you go back to the multisets?
Yeah, sure. Can try. Yeah.
So over here, the number of return, remove never exceed the number of called add. Even if this condition is true, it may so happen that you have more removes before the adds.
Yes, so this was for, wait. No, you cannot have more removes than adds even you have this.
So when you say multiset, it means the same value can be entered many times.
Yes, but if you remove, you remove one
and
of
it
them.
is, oh, sorry?
Yes, if you remove one of them.
And then can I remove again if I had
yes.
two?
So
okay.
if you add, remove is valid.
So, okay, what if the history is such that the first three are remove and then I see an add and they're all ordered like this, remove, 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 add, add, add. The numbers will be the same, but then it would
No, but you look at each, maybe this could have been more clear. So you look at each time point, the number that of returned removes and the complete and called adds.
Okay, so for
before
each prefix.
That. Yes, for each prefix.
And how do you talk about a prefix in a history? It's a partial order, so.
Yeah, I mean we can just well, the events are in total order. So each push, each call and return, these events form a total order.
Okay.
So we can just go through the events and count.
So when do I count a remove operation to be there? At the call time or at the return?
Return time.
I see. Okay. And can you go back to the queue?
Sure.
So over here.
Where?
Yeah. So next slide.
Next slide.
So over here the time complexity is n log n, and it is not just coming from the initial sorting of the.
No, I mean constructing the tree is n log n, and that's just one thing, and then it's plus this, where we do n searches, each is log n.
Okay, thank you. And one last question. So,
yes.
For stacks and queues, and even for multisets, I think, would you be able to carry out this exercise if you had peak operations?
So I do not know if these algorithms are very compatible with peak operations. Because, so right now so peak operations basically can act sort of like a similar as a pop operation in that it constrains it in the same way, that this actually has to be here now. But we would need to do some additional reasoning for that, and I don't know how to do that, at least not by extending these algorithms.
Thank you.
One more question.
Hi, so this is a bit of a tricky question, but since you did mention, so you mentioned that you have found some faults in the proofs of previous works.
Mm-hmm.
How confident are you in your current proofs?
I am fairly confident. I've written them and then done them again, and then had 2 or 3 people double check them. So I'm fairly certain.
Okay. And can you mention what's the actual bug you found in the previous proofs?
Okay, so well, the bug in a proof we found was, let's see if I remember the correct terminology. They presented a hornification procedure for what they called operation order specifications. And it turns out that this hornification procedure was not sound. And their proof for its soundness was incorrect.
Thank you.
One very short additional question.
Thank you. Eris Petrang from Technion. So when you say monitoring, do you mean that you go step by step, and when it's not linearizable, you shout, "This is not linearizable"? Okay. So did you try to look at not strong linearizable things where you simply don't know at the point?
So that's part of the future work, right? Related realistic conditions. No, snapshots is one line of work, right? Other structures, but then also other correctness conditions. So non-strong, weaker forms of linearizability.
Yeah, it's still linearizability. It just doesn't have an extra strong property. Maybe. I mean, there's a paper on strong linearizability.
Okay.
And there is a difference if you, at the end of the execution, you look for an order, or you know at any point if things have been linearized or not.
Okay. Yeah. Okay.
So.
Okay. Yeah. Okay.
And some snapshots are not like that.
No.
You cannot.
I'm not sure that even stacks are either.
No. These are strongly whatever you gave is strongly linearizable.
Okay.
Sorry, you probably should wrap up here because time is a little bit over. So let's thank the speaker again. Okay, the next talk is from Toplas, and it's about sound static data race verification for C. Is the race lost? The talk is going to be delivered by Caroline, right?
Yes.
Okay. Let's give her a very big hand.
Hello. So I will be talking about the sound static data race verification for C. So I will also start with a definition of data races. So our definition that we use is that there is a data race between two accesses A and B if the following condition holds. So the accesses are done to the same memory location. The accesses are done by different threads. At least one of the accesses is a write. At least one of the accesses is non-atomic. And there is no happens before relation between those accesses, so there's no synchronization. What is our dream is to have sound and static automated software verification of data race freedom. And what does this mean is that we want to verify data race freedom. We want to do this using sound static analysis tools. We want to verify the data race freedom in real world programs. And we want to do it automatically. So meaning with a push of a button, we want to reanalyze the program when it evolves. So after we have done the dynamic analysis and found all the bugs, fixed the bugs, we want to make sure that there are none left. So sound static data race freedom verification is a long-standing challenge for more than 20 years, but okay, I don't, yeah, okay. So, but the focus has traditionally been on lock-based synchronization. So the current tools handle lock-based synchronization rather well. So such examples as this function foo on the slide, where this data field is accessed, but the access is protected by the mutex, and if this is run by different threads, then everything is fine. But unfortunately, there's a big gap between the current benchmarks and the real-world programs. So what we have for current benchmark, the status quo benchmarks are the International Competition and Software Verification benchmark set. And this includes some 700 verification tasks, out of which only 2% are tasks where there is no tool that can handle them. So it can seem like everything is solved, but this is not the case. And why this has happened is because normally, as this benchmark set is compiled by community effort, all the benchmarks that get contributed are the ones from the evaluation packages, from the methods that they have done. So to bridge this gap, we asked our first research question: what are some concrete multi-threaded implementation idioms that prevent the existing verifiers from verifying data race freedom in real-world programs? So for this, we needed real-world programs, and we needed the verification tools, and then we ran them on them, and then we extracted the parts where these tools failed. So there are other works in the literature that we saw that run dynamic tools on C, read-over-tree programs and Java programs, as well as bugs have been extracted, the data race bugs from Golang language, but as far as we know, those idioms that are correct have not been extracted yet. So I will present the idioms first. So this is our main contribution. So let's focus on the right things to solve from now on so that we don't get distracted. So to ensure data race freedom in a program, the accesses must be separated either in space or in time. So on these idiom slides, I have 3 different ways how I say the same thing. So there's a textual representation, there's the idiom, the code, and then there's some visual representation on this time and space axis that shows the semantics of those idioms. So in this first example, so for space separated accesses, there are many ways how data is passed to the threads that ensures space separation. So in this example, syntactically, within the for loop, a fresh struct is created, and then this fresh struct is given to the worker thread. So each of the worker threads access their own fresh struct, so that ensures the separation in space. Another example of this data being passed to threads is now that the main thread creates an array, and then within the for loop passes an indexed address from this array to each thread. So each thread has their own part in this array that they access. So here we have this space separation. But in this example, there's also time separation involved, because on the line 4 here, the main thread actually writes to this array first. So there's a happens before relationship here. So before the main thread passes the ownership for this location in the array, it writes, and then the threads are able to write into this position. So this time and space can be intertwined there, and this makes proving these things even more difficult. So space separation can only also be ensured using thread local storage. So there's this thread specifier given by GCC that ensures that each of the threads have their own copy that they can modify, and this is ensured by construction. And then there's another specifier from the pthread library called pthread key, which can only store pointers, so there's an additional indirection here, but this is also ensured by construction, so each thread has their own copy that they can write to. So moving on to time-separated accesses, there are thread joining idioms. So here, syntactically, what happens is threads are created within a looping construct, and then the same threads are joined within a looping construct. So all of the accesses that the main thread does after the threads are joined are in a happens before relationship. So there's time separation. But the threads themselves, when they do accesses, there must be some synchronization, either it's locks or whatever. And then a variation of this is also, instead of joining the threads, there was a shared global integer where the main thread was counting how many threads are still alive. And then if that reached 0, then there's a happens before relationship again between the main thread and the worker threads. And there were also some other idioms that we saw for that ensured time separation. So these were based on value-based synchronization. So here, what happens is on line 18, main thread writes to a global variable. And then after this write, using synchronization, sets the ready flag to true. And then the worker threads will wait until the ready flag becomes true, and only then continue to read from this global variable. And in practice, this busy looping would be replaced by conditional variables. So now that we have seen some of those idioms that we are not able to handle yet while trying to prove data race freedom in C, there are more examples in the paper, but I will go briefly through the methodology that we used. So first of all, the data collection part. So for the real-world programs, we were fortunate to find an existing collection of real-world C programs that was compiled by Hong and Ryu, but we unfortunately had to exclude some of the programs for evaluation, so we were left with 18 programs, and the exclusion was because some of them were single-threaded, so there was no point in running the tools on them, and with the current static analysis tools, we cannot really handle projects where there are massive amounts of external code, so these wouldn't give meaningful results for us. So for the tools, we used tools that participate in the international competition on software verification SVComp from the no data race category, and these tools use various methods for trying to prove data race freedom in C. So there's abstract interpretation-based tools, model checking tools, and also satisfiability modulatory tools. And we acknowledge that these tools were not meant to be run on real-world programs. So this is quite depressing, but a lot of the results here, what you can see, are just blocked by engineering efforts. So, but we weren't really interested in this, what are the engineering efforts we want to do to get somewhere. So we actually, for this, we had to extract the idioms to see where they actually fail. We extracted those idioms, and then we asked our second research question, how well do existing verifiers handle each of those idioms when extracted into isolated microkernels? We did this because we wanted to validate that indeed these idioms that we extracted, the current methods cannot handle. So here are the results. So this table is a bit different than the table we saw before. Because for these micro examples, we know the ground truth. So we know that some small examples are indeed data race free, and then we also created racy variations of those programs. So here, unsound means that a verification tool, even if it proved the correct program correct, it also claimed the incorrect program to be correct, which we don't want because we want soundness. So there are a few, other than the unsound tools, there are a few ones that we can solve, but mostly we're not there yet. And for the third research question, we asked how prevalent are these challenging implementation idioms in real-world programs, because for the extraction part, we had to exclude some of the programs from the original set, but we actually wanted to include a larger set. So what we did, we took the syntactic markers of these idioms and we counted them in the whole benchmark set, including also the ones that we excluded for the actual tool evaluation. So here's the results for the prevalence. So for the subset on which we ran the tools, these are pretty okay, prevalent. Then for the whole concrete suit, what we are interested in here is that there is at least one or more of those syntactic markers also present in those programs that we excluded in our initial evaluation. And that is the case, which is nice. And also by the percentages, they are present in many of the benchmarks. And one thing that we also wanted to validate was that indeed in SVComp that we don't have these idioms yet. So in the SVComp benchmark set, we have a really good coverage of those locked-based synchronization tasks, but for some of those syntactic markers, there was 0 tasks that included them. So now we have contributed the extracted set also to the SVComp, and we hope that the tools will start to work on these problems and soon solve them. So to conclude, Log-based idioms are pretty well supported by current race detection tools, so we can prove data race freedom in programs that use log-based synchronization. However, real-world C programs actually rely on non-log-based idioms as well, and these idioms are poorly supported, and we should try to figure out new methods to support these idioms to get closer to verifying actual real-world code using static analysis tools. That's all. Thank you.
Thank you for a great talk. Any questions, comments? Okay, let me start. So you use the benchmark from the concrete work, and how concrete work for these benchmarks? I mean, did you evaluate concrete on the same research questions?
No, because I think they actually work on Rust, right? So
they somehow translate from C to Rust and verify the data race freedom there. So it kind of proves the absence of data races in C.
Yes, we didn't like independently evaluate them because we were really interested on, like, we want to go forward with having static analysis tools for C. So we want to still analyze C and do it on the C source without this translation. So that's our goal.
Okay. Yep. Any further questions? Yep.
Hi, this is Songwon from NYU. Thank you for the great talk. It gave me a really good idea of kind of the landscape today. I'm curious about benign data races as well, where that's kind of, I feel like that's something we haven't even started to look at. Do you see, across the different benchmark sets and kind of example code bases that you've looked at or examined, do you see any cases of benign data races that are either going undetected, which is, I guess, in some sense, good that benign data races are not are not recognized as errors, or do you see that benign data races are also kind of grouped into this set of potentially harmful behaviors?
Mm-hmm. So in our work, we consider all kinds of. So we also consider benign data races, but yes, I have seen a lot of, like, for example, logging messages. Like, well, if your log messages raise a bit, well, in the real world, we wouldn't care, but in this formal world, we do care. So we want to find them all and prove data race freedom for even benign data races.
One more question.
Could you elaborate a bit on this benign data race thing? I'm a little lost because I thought whenever there is a data race, it's always sort of like a violation of the compiler's guarantee or something. Namely, your code may be completely unpredictable. I think there was kind of a very good talk paper or something showing that in the world of C, there's no such thing called benign race, because you do not know what your compiler will do to your code whenever there is a race, right? Can you elaborate on that a little bit?
So for us, yes. So for abstract interpretation based on the work that we do, we consider benign data races and we want to be all correct. But the thing is, people have been moving away from soundness because the sound tools are not there yet to be applied on large-scale real-world programs. And then the first thing that gets left out are those benign races, because if you don't have a safety-critical system, you don't really care, because nobody, it's just a mindset that in the real world.
Yeah, I'm just a little bit confused by what is even a benign race. Like if I have a race, I don't know how the compiler is going to compile my program. Then how can I know whatever is benign or malicious? That's my confusion. But maybe we can talk off.
Yes, sure.
Yeah, let's thank the speaker again. Now it comes to the very final talk of this entire PLDI. Yusuke is going to talk about NOLA, later frequency state for verifying termination in arrays. Let's welcome the speaker.
Hello everyone, I'm Yusuke Matsushita from Kyoto University. Thank you all for coming here at the end of this conference. So now I'm really excited to talk about our work, NOLA. To start with, reasoning about program termination in the presence of shared mutable state is really hard. For example, let's think of the program called Landinzot. And here, R is a shared mutable reference to a function. Clearly, no loop appears in the program, but actually this program loops infinitely. This doesn't terminate. Why? This is because the reference R is set to a function that dereferences R and calls its body. So, in other words, self-reference is created by shared mutable state. This is the source of evil. Our work NOLA tackles this hard intersection of shared mutable state and termination. Before going technical, let me tell you the story behind the name NOLA. It's actually an acronymic nickname for New Orleans, Louisiana, which is known as the birthplace of jazz. This explains why we use the logo of a trumpet for our work NOLA. Also, in the city, there was Popol 2020, the first and last international conference that I attended before the pandemic. I miss the amazing time I had in the city. So now I'll give you a high-level overview of our work NOLA. Notably, the name NOLA also stands for the phrase, no later. What does that mean? Well, NOLA can help you finish your work soon, no later, maybe. Well, more technically, there's a feature called the later modality, denoted by the right-pointing triangle. It's a central but notorious feature of Iris, the well-known separation logic framework that you might have heard of. Remarkably, our work NOLA proposes a novel way to remove this later modality, which gives you the power to prove more things in Iris. Let me put it more precisely. The later modality in Iris originated from a strong mechanism for reasoning about shared mutable state, namely invariance and borrows. Iris used the later modality to make the logic sound in the presence of these features, but the modality is actually a fundamental obstacle to verification, especially of termination or liveness properties. NOLA enables you to remove the later modality while retaining the soundness, and empowers you to prove challenging properties like termination. Of course, our work is fully mechanized in Roc, and also as a library of Iris compatible with existing developments of Iris. So you can start using it now. Now, let's overview the motivation in more detail. Invariant, denoted by box P, so the box is part of the notation, and this roughly means that the situation described by the separation logic assertion P always holds. Remarkably, invariants are shareable, so they can be used to model the shared mutable state, especially the shared mutable reference type. Remarkably, this model of references can easily be nested simply because the invariant itself is a first-class separation logic or Iris proposition. We do need the invariant since we are in the world of separation logic, where an assertion like the points to token is not shareable, as it can be broken by state mutation. But there is a problem about the invariant. The naive invariant that you might expect is actually unsound. Naively, we expect this rule where P is preserved in the execution. But it's unsound. We cannot directly throw any SL assertion P in general. More concretely, there are paradoxes which are related to Landin's knot at a high level, which I showed you at the beginning. The known existing fix used by the current iris is to weaken the shared content by what is called the later modality. So they update the access rule of the invariant into this. In other words, this version of invariant asserts that the situation later P instead of just P always holds. To clarify this fact, in this talk, we write a gray later modality inside the box. The later modality weakens the proposition strictly, and it's not even transitive. This nature of the later modality avoids the paradoxes and brings the soundness, but it makes the invariant weaker than we naturally expect. In particular, there is a remaining challenge in termination and liveness verification due to the later modality from the invariant. More concretely, we cannot reason about the reference of shared mutable references. Recall that shared mutable references can be encoded using invariants, but now the invariant is weakened by the later modality. Due to this, when you dereference the reference, you come across the later modality, which actually blocks accessing the content of the reference. We note that this wasn't the case for the partial Hoare triple, which does not have the termination guarantee. Technically, it can internally strip off the later modality using a technique called step indexing. Unfortunately, it's well known that step indexing does not work well in termination and liveness verification. This is admitted by the paper of Similaris, a logic that targeted termination preservation. Similaris gave up the invariant due to this very reason. So, can we solve this frustrating situation? NOLA is here to solve this. Its key idea is so simple. Use syntax. Well, more precisely, syntax for separation logic assertions to share. So technically, syntax gives you better control of what can be shared in the invariant or such features, and to avoid paradoxes and achieve soundness. And this gives you better, finer control than the later modality. Long story short, the new invariant access rule in NOLA is this. Crucially, the invariant uses syntactic separation logic formulas to describe what can be stored. Also, syntactic formulas are embodied into iris propositions using the semantics function that is separately constructed. Remarkably, proofs themselves can be written semantically with usual iris propositions in iris. So NOLA uses syntax only for formulas, not proofs. You can use NOLA just as a library of iris in this sense. So I'll show how NOLA's use of syntax clears away the later modality. First, we just build a syntax for separation logic formulas and also define its semantics. For example, we can build syntax for formulas like this. Crucially, it includes the invariant. You can just define the semantics by structural induction like this. And importantly, this just works for the invariant. Now things are just later free. You can remodel the shared mutable reference type as a syntactic formula like this if you use NOLA. And this allows you to enjoy the later free access and make the dereference just work. As a verification example, we show infinite shared mutable lists as which even contain cyclic references. If we use NOLA, no later modality remains in the tail of the list, unlike iris. So we just enjoy the later free access. Thanks to this, we can verify termination of many things, including iteration over a list like this. And the proof just goes very naturally by like meta-logic induction and or like that. So you might wonder, why is NOLA sound? How is it expressive? Well-definedness of the semantics is actually the key to soundness. In particular, NOLA doesn't suffer from the paradoxes of London's knot. If you were to try to directly store the total whole triple into formulas, then you would have the ill-formed self-reference in the definition of the semantics. So this is actually rejected as a definition. Still, NOLA allows flexible construction for extra expressivity. For example, we can support advanced constructs like whole triples under the later modality subsuming the existing approach. Another way to support advanced constructs is stratification, where we have layers of separation logic formulas. To experts, I would like to advertise the power of SL formulas a bit more. First, we can actually store any semantics SL propositions under the later modality. So NOLA precisely subsumes the existing later weakened approach. Also, the set of SL formulas can even be extensible. This can be done by parameterizing the proof over the constructors to be used. This pretty much resembles how I plus sigma parameter works. To experts, I would also like to briefly mention that NOLA's model for the invariant just generalized Iris's model, as shown here. This gives a different view of how NOLA works. Remarkably, NOLA can also model Rust-style borrows in the style of the lifetime logic by the well-known work Rust Belt, but in the later free manner. In Rust, there is a feature called borrow, which is a sort of mutable state shared between the borrower and the lender. Long story short, NOLA can reason about Rust's borrow in the separation logic Iris like this. More technically, NOLA provides a set of proof rules like this. It's more advanced than the invariant, but the key idea of using SL formulas and its semantics is just the same. As a case study of NOLA, we built a prototype version of Rust Hold, a semantic foundation for verifying termination or total correctness for verifying termination. Or total correctness of Rust programs. For example, it can verify the total correctness of a Rust program that iterates over a list like this. Technically, it refines Rust home belt, an extension of Rust belt for functional correctness with NOLA's invariants and borrows. Notably, although syntax is used for semantic SL formulas for NOLA, we can build semantic typing or logical relation that enjoys extensibility. So this has a semantic model like this. I would also like to briefly mention recent work Lilo, which applied NOLA-style invariants to verify liveness under fair scheduling. Technically, it uses stratification to support higher order features. For example, Lilo can verify fair termination preservation like this. To experts, I would like to briefly tell you about our new finding, magic derivability, named so because it is so magical that I still don't fully understand how it works. So at the high level, it can be used for proving subtyping on shared mutable references semantically. Our magic derivability magically solves this beautifully by something roughly like a fixed point. This is quite cool stuff, so please read our paper for the details. So this is a summary of our work, NOLA. That's all for my talk. Thank you.
Any questions? Yeah.
Hi, I'm Zhong Shao from Yale University. Actually, 20 years ago, before people started to settle on using step indexing, there's actually lots of work on try to find a syntactic approach to reason about a high order feature like a first class code pointer, embedded reference. So there's this line of work my group did on XCAP, which actually, we use exactly the same syntax-based approach, and it was actually being used by, Adam Chipala's Bedrock and so on, around 15 years ago. So I wonder whether you are aware of that work, and if yes, what's the relationship?
Yeah, thank you for the pointer. So yeah, we are aware of that work actually, but we feel that the mechanism feature attained by that syntax approach of XCAP is kind of different from iris style invariance. So it's kind of different from shared mutable state in this sense, we would argue. So that's one difference. And also another difference is we pursue more extensibility or generality in this work. So yeah, we are aware that there's so many work studies to compare with NOLA, but we would say that NOLA is kind of one work that's kind of proposes really general approach of combining the iris world and the syntactic approach.
Okay, we can go offline, but I think it's clearly related, and I'm disappointed that your paper does not even cite our work as related.
Yeah, sorry.
Okay.
Hi, Simon Spice from Jane Street. Could you go back to slide 11, I think it was?
11, okay.
Yes, yeah, the example with the total Hort triple. Yes. If you were to put a total Hort triple into the invariant, you wouldn't be able to get rid of the later that now appears here, right?
You mean this model?
Yeah.
So yeah, so that's actually the problem. So if it were just partial Hort triple, then this definitely works by step indexing. And yeah, for total Hort triple, maybe we currently don't have a technique, but kind of thinking of solving that.
Right. Yep.
Yeah.
Thanks.
Further questions, comments?
Nick Swami from Microsoft Research. I'm just curious, in a way, by using this piece of syntax, you're kind of delimiting a universe of syntactically denotable iprops.
Mm-hmm.
Can you always do this? I mean, it seems like the cardinality of this thing would be too small in some cases.
You mean too small for some specific applications of verification?
Exactly.
I see. So yeah, that's a really good question, and so maybe short answer is we don't fully know the expressivity yet, and so. But one thing I can say is that so we can basically subsume the original iris approach using the later modality. So by combining that technique with the syntax, then probably we can verify more things, hopefully.
We tried this at some point in Pulse, trying to use syntax to break this the circularity, and examples like task pools, where a task refers to the task pool itself. I think we were not able to encode it via syntax. I wonder if your system can.
Okay. Yeah.
We can talk more.
Yeah. Let's talk offline. Yeah. That seems interesting. Thank you.
Probably it concludes the last session, and I'm not in a position to say that, but you are now formally dismissed.
I can say that.
Okay. Thank you all for coming to Korea.
Thank you.